Today we're diving deep into the mysterious realm of black holes, those cosmic giants that wield gravitational forces strong enough to bend the very fabric of space and time. Imagine this: massive dark spheres, 10 times the size of our sun, but millions of times heavier, lurking in the vast galaxies. But here's the kicker: they're not just rare phenomena. Recent discoveries show they're like VIPs of the cosmic scene, popping up in nearly every sizable galaxy out there. Telescopes worldwide, including the Swift Orbiting Observatory and robotic telescopes, focus on the celestial disturbance, determining its origin at a staggering 7.5 billion light years away. Recognizing this unprecedented event as the birth of a black hole, astronomers led by Tom Verstrand in New Mexico combined ground and space observations to conclude that the intense flash marked the culmination of a violent series of events within the core of a massive star. But let's not get ahead of ourselves. Today we are breaking down everything you need to know about black holes, from their formation to how they influence galaxies, and we even sneak peek into their role in the future of our universe. I'm Mike Adams, and welcome to All Things Space. A black hole is a region of space where light cannot escape its gravitational pull. Contrary to popular belief, a black hole isn't made of densely compacted matter. It's a point of extreme gravitational force surrounded by an event horizon. A black hole's legacy is its gravity, according to Einstein's theory of space-time warping. As a star's mass collapses, it punctures space-time, transforming matter's energy into a warped space-time energy. This energy can have profound effects on its surroundings, releasing astronomical energy when matter falls towards the black hole. Studying these energy emissions helps us understand the immense gravitational potential of black holes and how they shape the universe. Despite being shrouded in darkness, black holes reveal a history of powerful outbursts that scientists are diligently exploring, providing insights into the cosmos. Black holes were once thought to be rare, but recent surveys show that they're commonly found in the centers of large galaxies. The size of these black holes is linked to the size of the galaxy, suggesting they influence each other's development. To understand their role in the universe's evolution, astronomers use supercomputers to simulate cosmic history. Gravity attracted gas, forming stars and galaxies. Some stars exploded, likely creating the first black holes. Cosmologist Tiziano Di Matteo uses computer programs to simulate these processes, aiming to replicate the real universe. Observations by the Chandra X-ray Observatory reveal pairs of supermassive black holes in a dance of death. Einstein's theory explains that as black holes orbit each other, they create gravity waves, like ripples on a pond. When two black holes collide, they generate waves that carry away energy, causing them to merge. In simulations, black holes approaching one another create gravity waves drawing closer until merging occurs. Around halfway through the universe's existence, black holes reach peak growth by consuming significant gas during major mergers. Galaxies like our own Milky Way likely formed through merging and collisions as gravity initially brought together star and gas patches. The universe is replete with galaxies tearing apart and colliding, with each collision pushing objects into the gravitational pull of growing black holes. In the densest regions of the universe, a few black holes have become exceptionally large. Despite the violent processes, astronomers have deciphered clues about the universe's origins and planets like Earth by studying quasars, ultra-bright lights in the distant universe connected to energy emanating from galaxy centers and growing black holes. The mystery of how something without light can shine brightly has prompted investigation, leading to the launch of NASA's Fermi Gamma Ray Space Telescope near the Kennedy Space Center in Florida. This telescope aims to explore the role black holes play in shaping the universe. Observing and understanding the vast universe from Earth is an achievement for all humankind, as our ability to make meaningful measurements and develop a theoretical understanding encompasses the entire cosmos. Steve Ritz and his team investigate colossal black holes, focusing on their extraordinary growth billions of years ago at the center of galactic feeding frenzies. In regions densely packed with matter, young galaxies coalesced due to gravity, leading to the emergence of massive galaxies at their cores. The interaction with other galaxies caused these central black holes to expand immensely, sometimes reaching sizes billions of times that of our own sun. The rare expansion of supermassive black holes in the early universe, fueled by abundant gaseous inflows, shaped the cosmos, with powerful energy beams or jets extending tens of thousands of light years and impacting hosts of galaxies. Observations by the Chandra X-ray Observatory in the Perseus Galaxy Cluster reveal hot cavities carved from surrounding gas, hindering new star formation in the central region. Simultaneously, black hole jets seed surrounding regions with heavy elements, which are crucial for solar system formation. Telescopes like Fermi detect high-energy X-rays and gamma rays associated with these jets, offering valuable insight into their nature. The powerful jets result from spinning black holes, inducing a swirling motion, guided by magnetic fields as explained by Einstein's equations, enhancing our understanding of dynamic processes. Approaching black holes demands caution due to the intense gravitational forces. Smaller black holes can tear apart a starship, while supermassive ones, with their larger size and spread gravitational force, offer a gentler journey. Astrophysicist Andrew Hamilton likens matter falling into black holes to a turbulent river and waterfall, unveiling chaotic regions resembling a maelstrom. Objects near the event horizon must approach light speed to avoid falling in, and a spinning black hole may fling objects outward. Hamilton's visualization project, based on Einstein's equations, exposes the inner anatomy of black holes, revealing a chaotic region resembling a turbulent maelstrom. Despite theoretical ideas about cosmic tunnels called wormholes, connecting to white holes within black holes is unlikely due to the turbulent conditions within these cosmic entities. Within a black hole, unlike our familiar world, energy accumulates rather than dissipates. This leads to an extreme state called Planck density, surpassing anything in the universe, even hotter than our sun's core by trillions of times. Despite the extreme conditions, a black hole's energy release is constrained by its event horizon due to intense gravity. While supermassive black holes in our galaxy are currently considered calm, astronomers expect turbulence near their event horizons to unleash energy. The Andromeda galaxy, situated 2.5 million light-years away, is approaching our Milky Way at over 200,000 miles per hour. This journey will unfold over approximately 5 billion years. During this immense time frame, the Sun will transform, entering its twilight years and expanding, potentially affecting Earth. However, a more significant event awaits. Simulations of the impending collision between Andromeda and the Milky Way galaxies indicate a likely sequence of events. Initially, a close encounter will tear them apart due to mutual gravity. Our solar system is expected to be flung towards the celestial edges during this turmoil. As the galaxies eventually merge, their central supermassive black holes will spiral together, forming a larger black hole. Whether we will actually witness this celestial birth remains uncertain. In considering the future of our galaxy, astronomers ponder the destiny of matter and energy trapped within its central black hole. Will they endure indefinitely or succumb to the effects of time like other celestial bodies? In our present era, stars are the primary powerhouses of the universe. However, in trillions of years, stars will run out of fuel. They will fade, and the biggest ones will be pulled towards galaxy centers, eventually being consumed by supermassive black holes. The future envisions a universe dominated by remnants of dying stars and black holes. As stars burn out, they transform into neutron stars or white dwarfs. while black holes merge over extended periods, becoming the final strongholds of our universe. According to cosmologist Stephen Hawking's theory, black holes emit heat radiation due to quantum physics, gradually losing mass and leading to their eventual demise. While the last black hole disintegrates, it signifies the end of our known universe. Scientists are currently looking for evidence of black hole decay and exploring alternative methods such as observing black hole jets and inducing collisions in controlled lab conditions. The collimation process, starting with the blue ring, aims to generate energy by colliding small, high-energy fragments of fast protons. This collision concentrates enough energy to create tiny, extremely hot holes that rapidly radiate away. Monitoring indicators, including a barbecue reading of 1.2 to 1.3 times 10 to the ninth power, confirm positive feedback. Physicists at the Brookhaven National Lab propel gold atoms through extensive tunnels, accelerating them to a fraction of the speed of light. Collisions result in a fireball, generating extreme heat exceeding that of a supernova explosion. Creating a black hole requires more energy than Earth-bound colliders can provide. Alternative theories suggest the potential creation of black holes by colliding subatomic particles with potential experimentation at the Large Hadron Collider in Europe. Scientists ponder whether our universe is part of a more intricate cosmic reality beyond our daily dimension. Drawing an analogy to insects on a pond's surface, researchers explore the potential existence of extra dimensions intersecting with our world. High-energy particle collisions could reveal extra dimensions, potentially creating micro-black holes. Confirmation of a black hole's presence depends on observing the predicted shower of particles, according to Hawking's theory. This discovery could open a window to a deeper cosmic reality, emphasizing the richness of black hole research. Einstein's theory demonstrated the profound impact black holes have on generating extreme energies and are influencing the universe's structural dynamics. Recognizing black holes as fundamental to the workings of our universe represents a significant scientific breakthrough. If black holes do have a finite lifetime, their demise could signal the end of our universe. Some estimates suggest the largest black holes have a time horizon extending to Google years, an inconceivable yet finite span of time. The clock may be ticking in our universe, and the alarm will sound when the last black hole undergoes an explosion. Until next time, stay curious, keep exploring, and I'll see you in the next video.